Hi everyone, thank you for joining me on this webinar. We have 45 people online with us right now, and it's growing by the minute, but we will get started anyway. So the purpose of this webinar is to show how we can leverage IoT technologies to increase the reach of SCADA systems. And here's the agenda for today. Oh, where is it? Hold on. Yeah, there you go. All right, so the agenda for today, we will start with IoT 101, everything you need to know about IoT in a few slides. Then we'll remind ourselves who needs data anyway. We will then go and review industrial automation. In light of industrial IoT, we'll try to draw some lines between the two and discuss it. We will then review a few leading LP1 technologies. These are low-power technologies that are kind of replacing cellular technologies or working in parallel to cellular technologies. And eventually, we will discuss field to SCADA integration. Like Michelle said, there is the question box there on GoToWebinar, and you can type your questions in, and we will take them in different intervals during the presentation. So we will start with a review of the IoT. All right, so we're going to cover the basics. So the first question is, what is IoT? What is the Internet of Things? Is that something new, or perhaps it's something old with a new name, somewhat like rebranding or something? So it really depends who you ask. The industrial automation world kind of thinks that the IoT is a simple evolution of the classic industrial automation. Some other people and analysts think that the IoT, the Internet of Things, is the next revolution or is the current revolution. And I don't think there is any one good answer. It really depends. Now, for the sake of discussion here, we will use the following definition. We will just say that the IoT, the Internet of Things, is a hyper-connected ecosystem where you have things that could be any kind of objects, from a chair, a refrigerator, a car, or maybe some monitoring device at the source. You have gateways. These are devices that collect data from several different devices in the field and send them up to the cloud or to on-premises server. And then you have the software platforms. And then another thing to note about the IoT is that really it leverages state-of-the-art technologies. So if, for example, industrial IoT was more or less born around the 70s, this new wave of technologies that we have today, mainly low-cost and low-power electronics, really gives us the ability to go to places we couldn't go before, both in terms of cost and autonomous systems and so on. Another thing to note is the cloud-based platforms. So a lot of systems today run on the cloud, and whether it's Amazon Web Services or Rackspace or Google Cloud. So suddenly computation is not an issue. You can process tons of data using these platforms. That's another thing that contributed. In the consumer space and also a bit in the industrial space, smartphone apps are playing a vital role in this game. So in the past, if you had a piece of equipment and you would like someone to mess with it in the field, either you should have a laptop with a cable or you built your own terminal. But now today, you just you have a smartphone app and communicates with whatever device over Bluetooth, and you're done. Last thing worth mentioning here is the new radio standards. So maybe you heard the names Sigfox and LoRaWAN and NB-IoT. These radio standards kind of change the way we're able to send data from the field and also to send data to the field in some cases. And this really opens up opportunities that we couldn't really dream of, let's say, a few years back. The last thing to mention is that we're going to be generating data from all kinds of objects that we previously wouldn't imagine that we would even do that. I collected like a bunch of stuff, a bunch of things, for example. So here's the first one. This is a connected refrigerator. It looks kind of simple and cute. It tells you how hot is or what's the temperature in the fridge, whether the door is open or not, and so on. And a funny story that a month ago or so, there was this huge cyber attack that took Facebook, not Facebook, actually WhatsApp and other huge applications and internet players. It took it down, and what was behind that attack in some parts was refrigerators that were attacked by hackers and were used as a botnet to take these services down. So this is the kind of world that we're entering. This is a smart lock. It doesn't have a key. You open it with a Bluetooth app. That's also kind of like a nice application in the consumer world. This is a doorbell. Now, it's not only a doorbell. It's connected to the network, and you've got this nice camera here, so it can notify you on events that are happening in your house as you go. So this device as well is connected to the internet all the time, with the Wi-Fi at your house. This one is it's a connected fry pan that tells you what's the temperature and probably tons of other stuff about the thing that you are right now cooking. So you can argue whether, is this really useful and who needs it, but apparently people like that, and they fund these projects on Kickstarter and Indiegogo, and they push them forward. That's a connected trash bin. And the thing that you see here is actually a barcode scanner, so you can scan the boxes and the, of the stuff that you throw into the garbage, and then it kind of populates your shopping list. So that happens as well, and that's connected by Wi-Fi to your router at home, and then you get your shopping list. And this is really the next thing. So before actually dumping stuff into the trash, you can actually press this nice connected button from Amazon. And then Amazon will ship you something before it really runs out. So you can get these buttons and attach them to different items on your home, and then all you have to do is just press them, and you're good. And Amazon will ship you something. So we're that lazy nowadays. So this is the consumer IoT, consumer side of the IoT, but there's also the industrial side of the IoT. And here are some pictures of industrial things in the wild, right? So unlike the consumer side of the IoT, I would say that the industrial side is just a bit less sexy. We have sewers, we have water tanks, we have pumps, we have pipes running for miles and miles. We have canals, and we have fields and power grids. This is reality for us, okay? So Ayyeka operates in this field. This is how things looks in reality. It's not so cute as we think of, the little toys we saw before, or all these really cool devices. But this is how things look on the industrial side. Now, this kind of industrial equipment, the infrastructure, this is the infrastructure that actually takes care for all the precious resources that we have. It's water, it's power, oil, gas, the environment itself. It's all there. And a lot of people are working to make this infrastructure actually invisible, right? So if everything goes right and it's properly handled, people do not really notice this infrastructure. They just take it for granted. So people take for granted that water are running, that the roads are open and safe, and so on. And actually keeping this all running and safe is a big challenge, as some of you probably know. Here's a picture of the big picture, I call it, and you can see here different segments, different applications, different locations, devices, and tons of information. And it might be that you're not even able to read all this tiny text here, and that's exactly the point. The size of this Internet of Things it's huge, and people try to map it all the time and create these gigantic maps of what goes where and so on. Ayyeka, and specifically this webinar, is focusing on the industrial side. And according to some analysts, the industrial segment of the Internet of Things is more or less the same size of the consumer Internet of Things. Some say that it is bigger, some say that right now it's bigger, but then consumer will eventually prevail, but who knows. In terms of numbers, it's kind of scary. Okay, so if you Google, IoT number of devices projection, you will get probably 1,000 different graphs showing you something like this. All right, so something happened here, and then it explodes in the future. And all right, so this one, for example, tells us that by 2020 we're going to have 50 billion connected devices. All right, this one says something similar. I don't know if it's 2020 or 2025, but again, something around 50 billion connected devices. ranging from laptops, cell phones, and whatever gadgets and so on, including industrial and everything. This one is a bit more modest. It said that by 2020, and sorry for the resolution, by 2020, there are going to be only 30 billion devices, all right? Now, it doesn't really matter if it's going to be 50 billion, 30 billion, or just 10 billion. Just some math exercise that we're doing from time to time. Let's say we have to deploy 10 billion devices by 2020, and it takes 1 hour to deploy a single device. Let's say you have to put it in the sewers, you have to put it in the field, you have to drive somewhere, you have, I don't know what, even just to see that it works. That will take us 5 million working years to complete the deployment of these 10 billion devices. That's a lot, all right? It also tells you that something must change. It has to be easy to deploy these devices, and everything that we know about deploying stuff to remote locations must be streamlined in order to support these crazy numbers, even if they're wrong. Okay, so none of the projections here said it's going to be 10 billion. They said it's going to be 30 billion or 50 billion. But even if it's 10 billion, that's still a crazy amount of devices that has to go to the field. Of course, you can say, well, some of it will be industrial and some of it will be consumer. But again, the number is so big that even if you divide them by 10, it's still tons of work just to get these devices to the field and transmitting and so on. But the real impact is that we're going to have tons of data, literally tons of data. And we got to ask, all right, so in some cases, you might think, who needs this data? I don't know, in case of a smart trash bin or a fry pan, and maybe it's just me, maybe other people think that's critical to have. We got to ask, who needs more information, or what are the data drivers that push this industry forward? So real quick, well, data is the thing that we need in order to improve. If you have a problem, you collect data, you analyze it, you come up with solutions, you implement them, you reassess, and then you collect data again. Being blind in this world is kind of a bad idea. In the case of infrastructure, you're going to have some, I don't know, bridges might come down and water pipes might break and so on. Or you're going to be inefficient, and I will get to that in a minute. So another drivers for regulation for data is simply regulation. So regulation in many industries makes you collect and keep data and analyze it, and in some cases report it. Let's say you are running a sewer infrastructure, so you have to report overflows and so on. That's a requirement in some places. The infrastructure itself almost doesn't matter which industry. It's getting old, so it's getting really hard to support it. It's like running with a bucket full of holes, and the water is just zipping away. So you need more visibility and more information for what's going on in the field, just to make sure that things are okay. And lastly, optimization. Well, everyone wants to optimize their operation. Doesn't matter really what they're doing. So yeah, that's there. In terms of benefit, again, real quick, if you're a public entity, you would like to save money. If you're a private entity, you would like to make money. Everyone wants to improve the services and comply with regulation. And of course, there is enhanced asset management, which basically, if you do that, then you don't have to run to fail, like run your equipment to failure. You can do predictive maintenance and so on. All right. So that was like a quick overview of the IoT and some drivers for this segment. And I think we have a poll right now that we want to try on. Do we have it? All right, it's coming up. So you should see it. So please choose your answer. We'll give it a few seconds. You should see it on your screen popping up there. All right, yeah, so people are voting. 30%, 38%. 42%, 44%. All right, we're making progress here. So I will keep going as you vote. So we're now going to discuss industrial automation and industrial IoT. So, well, again, some people say that it's the same thing. Some people say it's completely two different things. In our opinion, it's more like of an evolution. It's just that the roots of the industries, the roots of the industrial automation, the roots of the industrial IoT, at least in our opinion, it's just different groups of people in different backgrounds, and that's why these industries evolve so differently. So what is a typical industrial automation setting? So a typical setting would be deployed in the perimeter, let's say the plant, the pump station, a factory, any site basically that is part of the operation. And one of the assumptions is that the power source, I mean, there is no problem finding a power source and communication lines into the SCADA system and servers. In most cases, industrial automation systems are set up to provide real-time data or nothing at all, and it reflects in the protocols and in the way that SCADA system process data. Either you get the data in real time or it's meaningless, basically. It also implies large data volumes and low latency that is required, and so on. Another thing is that industrial automation systems were basically designed to support thousands of devices, but not millions. Okay, so in a few slides ago, we showed that slide with the explosion of devices going to 50 billions or 10 billions, doesn't matter. So it's quite clear that given the classic industrial automation protocols and systems, we're not going to get there. If, for a few examples, if you're using Modbus as a protocol to daisy chain sensors, so you can have up to 247 devices. That's it. You cannot scale beyond that on the same bus. And the MP3 can support 65,000 devices, but it's not millions. It's not designed for millions of devices. And then it also requires a high level of expertise just to deploy the equipment to the field. If it's a PLC, you have to know how to program that. If it's an RTU, you probably have, I don't know, anything between 20 to 200 configurations to complete before you can actually operate it and connect it and so on. So you got to master it. It's not a game for everyone to play in. By the way, did we close the poll? All right, we closed the poll. So the poll asks how many tags do you have in your SCADA, and it looks like we have 30% of the attendees. They have something between 1,000 and 10,000 tags on the SCADA system, and the rest are kind of negligible. So, and we have like 40% that do not use SCADA system. So it tells you again, you see that the majority of the attendees here do not have anything above 10,000 tags in their SCADA system, which by definition says that they do not have more than 10,000 devices in the field. This is quite typical for industrial automation, all right, given the cost and the complexity of the deployment. What about cybersecurity? Well, that was not part of the plan. When you look at classic industrial automation protocols, it's just not there. Modbus is plain text, open, no encryption, no authentication, and so on. And other protocols suffer a different level of this phenomena. It was just not considered when they designed it. If you look at a classic industrial automation setup, so usually you have the plant itself. So here it is. That's our plant or factory or treatment plant, or I don't know, could be anything. There you have the SCADA system with all the goodies of the industrial automation where you can control stuff, start and stop. And then you have the rest of the world where you have nada. So we have SCADA and nada, all right? And the transition from nada to SCADA, it's exactly what it's all about, actually. If we look in terms of segments that are leading the nada field data phenomena, so we have basically almost every industry, but I'd like to point some of them. So oil and gas, water and wastewater, agriculture, power, smart cities, civil engineering. The common thing for all these industries is that they have dispersed assets and linear infrastructure that stretches for 1,000 miles. All right, imagine the I don't know how many miles of road you have in the United States, but it's a lot. And if you have to monitor even 1% of them, then that's a huge operation. Same for power, same for water, same for sewer, oil and gas, and so on. These are huge infrastructure, and if you need to cover them, then that's a big project. And I would like to touch some points as to why field data collection is challenging in dispersed, given the dispersed asset scenario. So the first thing is power supply. Deploying devices to the field without having a constant power supply, it is a big deal. I know that you all think that we're carrying these smartphones and they run and we're connected and whatever, but remember, you charge your iPhone or your smartphone at least once a day. If you cannot do that, then you have a problem. So some of you might think, all right, what about solar panels and turbines and maybe turbines in the pipes and so on? Yes, that could work in some of the places, but solar panels do not work underground, and they also they're not that good with hurricanes. Turbines are a big deal to install and so on. And again, remember, if it takes too long to install, or if you need a permit to put some kind of pole in the middle of the street to mount a solar panel, then you're in big trouble. That's the main motivation for having an independent power source for deployment. It makes things easier, and you can deploy it everywhere. The next thing is integration. So you have to figure out a lot of stuff in order to get it done properly, ranging from what kind of output does the sensors have. It could be a current loop, or it could be a voltage output. It could be, sorry, can you hear me well? All right. So sensors has different interfaces. Different cellular operators have different settings. Different SCADA systems use different protocols, and getting it all together requires a lot of expertise in different fields. And also, you know, just estimating the power budget of the system. It depends on the communication. It depends on the sensor. It depends on the way you operate the device, and so on. So there's a lot of integration here. Communication, that's another thing to figure out, both from the point of view of configuration, and you know, just a simple fact that they didn't deploy Ethernet along the sewers and along the water pipes and along the roads. So it has to be wireless, and then you know, you have all sorts of different options, but none of them are trivial to operate. So it looks trivial because our smartphones are, you know, connecting everywhere, and we land somewhere and everything works. But in reality, when you get to the bits and the bytes and everything must tick, then it is challenging. Lastly, there is cybersecurity, which is a big deal today, and it wasn't a big deal 20 or 30 years ago. And that's why you see a lot of companies and a lot of utilities offering very interesting and very smart products to make these solutions, the classic industrial solutions, safer for use. And I think there are too many incidents nowadays to count on this area, but that's a big deal today. All right, so now let's go to industrial IoT and try to identify what makes it an industrial IoT technology. So I'd say it's same but different, right? So it's basically almost the same problems, but different tool sets. So in my opinion, at least, it's deployed everywhere. If you show me a device and it's not really network wireless or network connected, I would probably lean to say that's not an IoT device. Well, again, there is no clear definition, and who am I to say that? But a typical IoT device would be wireless. Most of the designs that you saw, both on the consumer side and the designs that you see today, the devices that you see today on the industrial IoT, most of them are just wireless, and it makes sense. Also, historical data is treated natively, unlike the classic industrial automation where the data has to be real-time or it has almost no value. So let's say in this setting of industrial IoT, it's okay to report historical data. It's okay to collect data every minute and then report it once a day. Okay, then the challenge is how do you push that to the SCADA, but we'll get to that. All right. Again, it's designed to support millions of devices, not just thousands. And again, it reflects on the protocols themselves. Plug-and-play approach. It has to be easy, and you see that the solutions that people offer today in this segment, in this market, are leaning to that approach. It's not always easy, but it's improving over time. One example for that is having SIM cards that simply work everywhere. You don't have to choose a SIM card per state that you're shipping your device. You have global SIM cards and so on. That's one example for that. And of course, it was designed with cybersecurity in mind, simply because it was designed, you know, just in the past, I don't know, 2 to 5 years, let's say, in the internet era. So it means that basically you can leverage all the internet technologies that we know, TLS and encryption, authentication, everything that is out there. You can leverage that. And that's great. All right, I will now review a few IoT technologies in the context of industrial IoT. First, there are the low power wide area networks, LP1. It's hard to miss them on LinkedIn and on tech publications. Doesn't matter which one you read, you probably at some point heard someone mentioning one of them. So these are new radio technologies, and we will go in depth into them. Then I will describe MQTT. That's a protocol that might serve as a replacement for the classic industrial automation protocols, OPC and DNP3, and we will get into that. And of course, there are edge devices. We won't have a lot of time. Oh, disconnected again. Can you hear me? All right, sorry, I have some audio issues. And edge devices, as times allow, I will present some. All right, so let's dive into LP1 technologies. So we'll begin with the motivation of LP1. Who needs low power wide area network? Because we do have 3G and 4G, and it's great, and it's almost everywhere. But it was designed for high bandwidth, and for uploading videos into Facebook, YouTube, and tweeting stuff, and posting images on Facebook. But in reality, industrial or just IoT devices consume just a tiny bit of data every month. These 3 megabytes that I mentioned here, it's our statistics over thousands of devices that we have. That's all we do. And just to give you an idea of how much data is that, I would say one picture that you upload into Facebook is probably what our device makes in a month. All right, so it's that ridiculous. And I think one of the most constraining elements of using 3G and 4G is the power consumption. It really kills the battery. And in order to get a really long battery life on 3G and 4G, you have to do a lot of work. You have to think out of the box and kind of twist and bend the technology to work for you. Lastly, the technology is expensive, because you have this crazy technology that can send tons of data in seconds, literally live video from everywhere over the air. Then that's quite smart, and that costs money. And also the certification itself is kind of expensive. And what's frustrating is that for really tiny industrial IoT devices, we don't need all of that. We don't have battery. We don't have the energy to spend on huge bandwidth that we don't even use. And everyone wants devices that are low cost and affordable. If you're thinking satellite, then the answer is no. That's too expensive. And in reality, it's only used when you have no other choice. And by no other choice is either there is no cellular coverage, or you have to have some kind of independent redundancy, which is not cellular. I would just mention that our devices, for example, we have cellular redundancy. For example, in the States, we're using both AT&T and Verizon on the same device, so you don't have to choose which network operator you're using. It's the same device, and it will switch automatically between them. So if AT&T goes down, and it doesn't happen so often, then it will automatically switch to Verizon, as an example. You could also deploy private radio networks, but the deployment and maintenance of these are pretty crazy, and it used to be something that people did a lot in the past and kind of fading away these days. I will now dig into the first technology. We'll talk about Sigfox a bit. So first of all, Sigfox is a technology company and a network operator. So they develop both the technology, the standard itself, and they're also operating the network, at least in the United States. In different parts of the world, Sigfox is franchising the network or letting other operators run it, but basically it's one global network. An important thing to know, it operates in the ISM bands. These are the unlicensed bands. ISM stands for industrial, scientific, and medical. So it means everyone can use these bands for whatever use they want, including Sigfox. But there is no real control of what's going on in these bands. Sigfox is an ultra low bandwidth technology, or ultra narrow band, sometimes it's called. A device can send to the cloud 100 tiny messages per day. When I say tiny message, I mean something like a timestamp and a value. All right. The cloud can send a device 4 tiny messages per day, so that's really nothing. Something on the order of a reboot command, but nothing else really. The good news is that the modem costs are much lower comparing to 3G and 4G, and then Another thing to note is that currently, although Sigfox is investing a lot of efforts into deploying and covering nationwide in the States and other places, it takes time. So they're making progress. We see the progress. You can see it online on their website. But it's not anywhere near the coverage that the cellular operators have currently in almost everywhere in the world. The good news is that Sigfox really responds quickly to demand. So if you have a project and you say, well, I wish I had Sigfox here, they might actually set up that, that coverage for you within a few weeks. Next technology is LoRaWAN, or in short, people just call it LoRa. Unlike Sigfox, LoRa is just a standard. It's a promising open radio standard that covers a bit more than just the radio itself. But it's an alliance. It's not a single company. All right. So in theory, every member of the LoRa alliance can implement it and develop hardware that is supporting this technology and so on. It also operates in the ISM band. So again, anyone can operate in these bands. They're not controlled and they're not licensed by the government. The bandwidth is marginally better than Sigfox. In theory, it's a whole lot better, but what we experience and hear from all around is that in reality, well, it's better, but not that better. So you can send the messages, you can say, let's say they are on the order of bytes, tens of bytes, let's say. So you can have, I don't know, 10 samples and timestamps in one packet. The deployment, unlike Sigfox again, is supposed to be by the end users or integrators. So if Sigfox is trying to provide nationwide cover, in LoRa is not the case. There is, however, one company called CNET, which is trying to cover the US nationwide with LoRa, and some people call it the Sigfox of LoRa, for lack of a better description. So they take the LoRa standard and try to deploy it nationwide. The last technologies in the LP1 section are NB-IoT and LTE Cat-M, and this is a bit confusing. They're both part of the LTE family, so to speak. These are new standards, and this is the cellular operators' answer to Sigfox and LoRa. So the groups that are defining the cellular standards, basically for, let's say, the past decade, we're focusing on high bandwidth video, online chats, and so on application. They completely missed the narrow band market and IoT devices. And now they're trying to correct for that. And they're trying to correct by introducing two new standards. One is called NB-IoT and the other one is Cat-M. And they are supposed to do something similar to what Sigfox and LoRaWAN are trying to do. Some people call them the Sigfox killer or LoRa killer. We don't see it this way. We think it's a complementary product and not something that will completely kill Sigfox and LoRa. Unlike Sigfox and LoRa, NB-IoT and Cat-M operate in the license band, just like your cellular phone is operating in the license band. This gives a better chance for availability because you can expect less interference in these bands. Another thing to note is that the bandwidth is significantly better. I mean better. There is more bandwidth there. Better or not depends on the application. But of course, it comes with a price. The energy consumption is of course expected to be larger simply because you're pushing more bits into the air. However, in terms of coverage, well, it's as good as cellular once the rollout starts, right? So the plan right now, as we see it, is to cover Europe. The plan of Deutsche Telekom and Vodafone and these guys is to cover Europe with NB-IoT. And Verizon already and AT&T both already declared that they deploying LTE Cat-M in the United States. The stage of the deployment, it's hard to tell where is it. How does it go right now? Almost all the operators said that by end of 2017, the networks are going to be up and running. It's kind of the chicken and an egg. No one wants to deploy before there are devices. There will be no devices before the network will be there, and so on. But it's coming anyway. I would like to present a quick case study. This is the installation of Sigfox-enabled devices from Ayyeka in San Francisco. These devices, well, the story there is that they have seawater infiltrating their sewers, and that's kind of a bad thing, and it kills the treatment plant, basically. So they have to monitor it, and they had to collect conductivity and level readings from the sewers. So here at the bottom, you can see the installation process. Getting stuff into the sewer. Getting stuff into the sewer is not a simple task. That's our device there. That's the wavelet device. So the devices there are actually using both Sigfox and cellular at the same time. We're using Sigfox to push data every few minutes, in this case every 5 minutes, and then we're using cellular to do the rest of the stuff. And what's the rest of the stuff? For example, configuration of the device, upgrades, and also sending data that you simply cannot send over Sigfox. So for example, if I have too much data, I can choose to send one of the streams on Sigfox, and the rest of the streams I will just simply send over the cellular, I don't know, 4 times a day, but not every 5 minutes, all right? So we're kind of trying to benefit from both worlds, and we also have redundancy. If something happens to Sigfox, we still have cellular. If something happens to the cellular, again, all the operators in cellular, we still have Sigfox transmitting. All right, so that concludes our LP1 section. I think it's a good time to take some questions. Do we have any questions?
Yep. So if you have additional questions, please just type it in the chat box, or you can unmute yourself and ask in person. We had a question come in earlier about the number of the prediction on the number of devices. So here's the question. It's more of a clarification, I think. It says that there's a firm definition for IoT. It must be an ecosystem in which the devices use information from cloud-based sources. Remote control for appliance from a smartphone is not IoT. So just wanted to get your insight on that, Yair. More of a...
All right, so I'd say that from my point of view, sorry, there is this echo. So from my point of view, and for all I am reading and conferences that I'm attending, I'm hearing so many different definitions that's really hard to point, what is exactly an IoT device and what is exactly the IoT. There is several things that everyone agrees, and that it's going to be big, and you can see that from the trends, unless everyone is wrong about the amount of devices. And about the rest of it, well, it's hard to say. Whether something that is connected by cable is an IoT device or not. Well, some people say yes, some people say no. I cannot really say, what is that? In my opinion, it's definitely an ecosystem. I do not agree with the definition that it has to be cloud-based. And if you read about the projections of, what's the place that LoRa, for example, is going to take in a world where you have NB-IoT and Cat-M, then one of the projections is that LoRa is going to serve private networks and private facilities for radio technology. Does this mean that LoRa is no longer an IoT technology? I don't think so. So, in my opinion, the definition is still open. All right, we'll get going. The next part is how to get data from the field to the SCADA. And we'll go real quick about it. So we have, if you're looking at a bunch of how do you integrate sensors into devices, and by the way, this is our wavelet device here. So you have sensors. Sensors usually have standard protocols in which they communicate with devices that collect the data from. So it could be current loops, it could be voltage output, it could be Modbus RTU, it could be SDI12 and digital IOs. And then, for example, this is our device, so it collects the data from the sensors, samples it, timestamps the data, store it locally, and then somehow we need to get the data into the SCADA. And the question is how exactly? So here's one option. One option is Modbus, and the short answer is no. Okay. The idea of Modbus basically was to create a unified interface for industrial equipment, and it does that perfectly. Also between different servers, but it was not really designed for large-scale deployments. Okay, so Modbus was really designed for local networks, whether they're serial cables running across the facility or a TCP/IP network. Still is a local network. You can use Modbus with VPNs, but again, it was not designed for that. Some things that you cannot do with Modbus is, for example, or at least shouldn't try, it's remote firmware upgrades. Well, there's no simple way to do it. And of course, cybersecurity features are just not part of the standard at all. And again, you know, as to all industrial automation protocols, the devices, the remote devices, the slaves, in case of Modbus, are expected to be online. And that's kind of problematic for devices that are running on batteries. All right, so if not Modbus, we can try OPC to get data from the field to the SCADA. So just a reminder, OPC was born somewhere around 96 as a heavily dependent Windows technology. It was based on COM and DCOM from Microsoft. A newer standard was developed in 2006, and we're still seeing SCADA systems that are adopting it. So it's only 10 years old, so it's kind of new here. But OPC UA has really new features that are nice. But again, the acceptance of that and the support in the field is kind of crawling slowly. OPC was originally designed for real-time data collection and control. So it is based on TCP/IP network or designed for TCP/IP network. So I would say the internet is the limit, right? You can take it everywhere. But again, the classic OPC is not encrypted and should not be used over the internet. The new versions of OPC are better. Historical data, timestamp data, it was not part of the original OPC DA protocol. It was added later, and usually it requires additional licensing on the SCADA side. So again, it's not something that most people or most installations that we see are actually happy to work with. And again, remote devices are expected to be online. So again, OPC is not designed for offline devices. Sorry. Okay, so here's another candidate. That's DMP3. It's a little more. It's newer than OPC, I would say, and it's being still adopted. It's not so popular in the wastewater industry. It is popular in the power segment and other industrial segments. Same idea as OPC, but better. It does support natively timestamp data, so you can push natively historical data into the SCADA system. It supports encryption, although from our experience, in most of the cases that we encountered, people did not set it up, sadly. It also supports remote upgrades and sending files, but again, in most cases, people do not use that. And again, devices are expected to be online. If they're not online, then it's an issue, usually. So these were three classic industrial automation protocols. I'm now going to talk about MQTT, which it's something you probably heard because there is a lot of buzz around it. I'm going to try to explain what is MQTT and how is it going to participate in the solution. It's not solving everything, but it's part of the solution. So MQTT stands for Message Queue Telemetry Transport. It was developed originally by IBM as part of their MQ series software products, and then later evolved into an open standard. But the first thing to note is that it's a transport protocol. It's not a complete solution, okay? We deliver messages from point A to point B, or maybe sometimes multiple destinations, but the content of the messages could be anything. So it's just like, if you have to imagine, it's just like having a FedEx courier. You give the courier your package, and then it delivers it. What's in the package? It depends. It could be the latest news broadcast, or it could be data that is related to SCADA or whatever. So again, it's just a transfer protocol. It does not solve the entire thing. It is designed for constrained devices. So it was designed such that it would fit into tiny devices running on batteries with limited network bandwidth. So the protocol itself is really simple. You can read it in something like 2 hours, end to end. And also it leverages all the really cool technologies that we see today, TLS and everything. Just really quickly how it works. So you have, it works with a publish-subscribe model. So the idea is that clients and servers simply leave messages to each other, and then messages can be picked up at any time. So the devices suddenly do not need to be online, and that's the benefit that we have from that. If you'd like, it's like the invention of the voicemail, just in communication protocols, right? So you can just leave your messages there. Now, if you try to put a finger on the problem, so this is the problem. What we painted here as the industrial IoT world and the SCADA world do not really speak the same language in many cases. At least not according to the definition that we use here, okay? So SCADA systems use their classic industrial automation protocols, and at least what we described here, so IoT devices use MQTT and HTTP and TLS, and they're not exactly compatible. So this is the point to introduce our wavelet device. So there you see it, wavelet. It's a battery-powered device. It's ruggedized. It's IP68. An industrial IoT device. It has interfaces probably to, let's say, 90% of the sensors you can have out there. It supports multi-radio technologies, both cellular and LP1, and it can do a lot of stuff. So how does this help us to put things together? So we begin with reading data from the sensors with all sorts of different inputs. Once we read the data and we timestamp it locally and store it locally, we normalize it. We store it in a certain way that anything past this point doesn't really care if it's an analog input or a serial input, okay? And then we can use either HTTP or MQTT to push the data into our software stack right here. And we do that over various network technologies. And then to push the data into the SCADA, we leverage current protocols, so DMP3 and OPC UA, if that's acceptable, CSV files if all hell broke loose, and MQTT, which is basically coming up because for now we see a lot of noise around this, but not too many implementations in the field. But that's definitely the future for us. In terms of system architecture, so there are several solutions. If you can do without a SCADA system for some reason, then you can have your devices in the field and then enjoy our cloud hosting, and then either consume the data in the browser or through the API. We have SOAP APIs and RESTful APIs. This is a hybrid cloud architecture. So you have the devices, and then you have our cloud, and then from the customer's network, we isolate a single computer where we deploy our SCADA connector, and this is in the demilitarized zone, the DMZ of the client's network. And this piece of software actually reaches out to our cloud, pulls the data, and then pushes it in to the SCADA system. How does it push to the SCADA system? Again, either DMP3 or OPC or CSV files, and soon to be MQTT. Lastly, if your cybersecurity policy do not allow you to use cloud at all, which is quite common in the industrial world, then you can have the devices transmit directly to your network. Without going through our cloud, you would still need our connector right here, and then we will push the data to the SCADA. And by that, I would like to summarize our webinar. Really 3 points. So the industrial IoT and the industrial automation world are really converging. If you have to ask me, then I think that the reason that they are defined in some cases differently and they're using different views of the world, it's probably because different people with different backgrounds in different times designed them. But ultimately, I would say it's basically trying to solve the same problem. Get data from the field, control devices in the field, and so on. As I said, industrial IoT can be used to extend the reach of classic SCADA systems. In order to do so, we have to do some manipulations, sometimes change protocols and some integrations. But it is definitely possible, and we've been quite successful doing that so far. The technology stack itself is quite complicated. It requires a lot of different disciplines to master. And it has to be streamlined to facilitate the mass deployment that people project for the IoT. But all in all, we see that it is going this way with lighter protocol and the cost reductions and energy efficient technologies and so on. So I'm happy to take any questions you have right now. Do you have any more questions? We do?
So there are a number of questions that came in. We also just opened up a poll. If you take a look at the right sidebar there. So I'm going to start asking the questions while you're answering the poll. This goes back to the communication technologies. We had a question from Charlie Platt about what about Zigbee?
Yeah, so Zigbee is a mesh radio communication network. And sorry, we had a second. Okay, so Zigbee is a mesh radio communication network. Mesh means that you deploy a lot of devices and they transmit the signals. The data actually hops from one device to another until it reaches the final destination of that data packet. We know that there have been a lot of deployments, some of them in the AMR, the automatic meter reading fields, and so on. And they're mainly suitable for dense, really dense deployments. So if you have, I don't know, hundreds of nodes within 1 square mile, great. If you have 5 nodes in 1 square mile, that might not work if you're within the city or underground. We also, from our experience, from what we see from our customers, they're not really interested in deploying the networks themselves. It's not what they do for a living. Our customers, at least, focus on running the infrastructure, and they would like to enjoy, or let's say, they wouldn't like to be in charge of their own radio network. So I wouldn't say mesh networks are dead. They're just, being used in certain scenarios. And from our experience, if you're in the water or oil and gas in dispersed assets in the middle of nowhere, where you might have less than one monitoring site per square kilometer, and so on, then it doesn't make a lot of sense to use that technology.
So we have another question about what protocols are required, and the asker wants to know, can we simply just use 4 to 20 milliamps output, and explains that she's new to SCADA.
Sorry.
The asker wants to know what kind of protocols are required, sensor protocols, and they want to know if they can use 4 to 20 milliamps, and explain that they're new to SCADA.
Yeah. All right, so 4 to 20 is a protocol that was designed to get signals from sensors into the SCADA. In the past, it was done directly. In some places, they still do it. They have, on the SCADA server itself, there are interface cards that can read the 4 to 20 milliamps current output. But if you have sensors at the field and you would like to get that signal to the SCADA, you have to have some kind of device that will read that current output and then convert it to something that it can send over the air and then get that to the SCADA. This is something that our device, for example, does. And it's definitely possible to use it. I would say, when you have simple sensors, let's say, I don't know, pressure transducer or just flow monitors and so on, flow meters, sorry. So that output is probably the most common output. All right. So the answer is 100% yes.
If there's just one more question we can take till we have to close down. All right, I think that's it for today. Thank you all for joining us. If you have any feedback, questions, comments, please let us know. Shoot us an email. And we appreciate your participation, and we'll send you more information about our upcoming webinars. Thanks again.
Thank you, everyone.